The following graph describes an airplane's distance from its last point of rest. Is the plane's velocity greater at t equals 6 seconds or t equals 20 seconds, and how can you tell? We know that the velocity is the derivative of the position. Since we are looking at a graph of the position function, we're interested in looking at the slope of the tangent line at both time t equals 6 seconds and time t equals 20 seconds, and we want to compare the slopes at each of those points. Now I have drawn the tangent line at each of these points, at time t equals 6 and also at time t equals 20. Looking at those tangent lines to the curve, which line has a greater slope? At time t equals 20, the slope of that tangent line is greater. It is steeper than the slope of the line at time t equals 6. So therefore the velocity is greater at time t equals 20 because the slope of that tangent line is greater. So we can conclude that the velocity at time t equals 20 seconds is greater since the slope of the tangent line is greater there. For part B, we're asked, is the plane's acceleration positive or negative? How can you tell? We know that the acceleration is the derivative of the velocity. So we need to think about how is the velocity changing over time? Since the velocity is the slope of the tangent lines to the curve in the graph, we need to ask ourselves, how are those slopes of those tangent lines changing over time? Now I have drawn some tangent lines to the curve, and what I want us to do is think about what's happening to the slope of these tangent lines. As time goes on, increases, notice that the slope of each of these tangent lines is also increasing. It's getting steeper and steeper. Since the slope is increasing and getting larger and steeper, we know that the acceleration is positive because the velocity is increasing. So we can conclude that the acceleration is positive since the velocity, also the slope of the tangent line, is increasing over time. Nadia's Fashions discovers that the number of items sold T days after launching a new sales promotion is given by n of t, which is equal to 2t cubed minus 3t squared plus 2t. We're asked to find the derivative at t equal 1, t equal 2, and t equal 4. So let's first begin by finding the derivative of this function with respect to t. Using the power rule, the derivative is 6t squared minus 6t plus 2. Now we want to find the derivative when t is equal to 1. So we're going to plug 1 in for t. So we have 6 times 1 squared minus 6 times 1 plus 2. So simplifying, we have a 6 minus 6 plus 2, so we get an answer of 2. Remember that the derivative gives us the rate of change. So our answer then is 2 items per day. Now we're finding the derivative when t equals 2. So n prime of 2, so we're plugging 2 into the function. 6 times 2 squared minus 6 times 2 plus 2. Simplifying, we have 24 minus 12 plus 2, which is going to be 14. So our answer then is 14 items per day. That is the rate of change at time t equal 2. Next, we're finding the derivative when t equals 4. So we're taking n prime of 4, plugging 4 in for t. 6 times 4 squared minus 6 times 4 plus 2. This is going to simplify and give us 74. So here's 74 items per day is the rate of change at 4 days. For part B, we're asked to find the second derivative for time t equal 1, t equal 2, and t equal 4. Well, in part A, we found the first derivative to be n prime of t equal to 6t squared minus 6t plus 2. So now to get the second derivative, we're going to take the derivative of the first. So n double prime then, using the power rule on the first derivative, is going to give us a 12t minus 6. So next we're going to evaluate the second derivative at time t equal 1. So plugging 1 into the second derivative, we have 12 times 1 minus 6, which is going to give us 6. Okay, so now what does this answer mean? Well, after 1 day, the rate of sales is increasing at 6 items per day per day. So in other words, the rate at which sales are increasing is increasing. Next, let's find the second derivative at time t equal 2. So plugging 2 into the second derivative, we have 12 times 2 minus 6. So this is going to give us 24 minus 6, which is 18. So here we have 18 items per day per day. So here the rate at which sales are increasing even more at time t equal 2, at 2 days. The rate of sales is increasing at 18 items per day per day. Next, we're going to find the second derivative at time t equal 4. So plugging 4 into the second derivative, we have 12 times 4 minus 6, which is going to give us 42 items per day squared. So here the rate of sales is increasing at 42 items per day per day. So in other words, the rate at which sales are increasing is increasing. On the moon, all free fall distance functions are of the form s sub t equal to 0.81 t squared, where t is in seconds and s sub t is in meters. An object is dropped from a height of 200 meters above the moon. After t equal 2 seconds, how far has the object fallen? Asking how far the object has fallen is equivalent to asking what is the object's position after 2 seconds. So we're going to plug 2 into our position function, which is given to us. So we have 0.81 times 2 squared. So simplifying this, we get an answer of 3.24 meters is how far the object has fallen after 2 seconds. Next, for part B, we're asked how fast is it traveling? Well, that's equivalent to asking what is the velocity? So we need to find the derivative of the position function. So we're finding the velocity with respect to t, which is equivalent to taking the derivative of the position function. So taking the derivative, using the power rule, we have 2 times 0.81 t to the first power, which simplifies to give us 1.62 t. Now how fast is it traveling at t equal 2? So we're going to plug 2 into the velocity function. So we have 1.62 times 2, which gives us 3.24 meters per second. So that is the object's velocity. It is 3.24 meters per second. Next, we're asked to find what is its acceleration. Well, acceleration, we can call it a sub t, is the derivative of the velocity function. And the derivative of the velocity is the second derivative of the position function. Well, we already found the velocity function in part B. So using the velocity function, which we found to be 1.62 t, we need to take the derivative of that to get acceleration. So acceleration then, taking the derivative of the velocity, is going to be 1.62 meters per second squared. This constant is also referred to as the gravitational constant for the moon.